Russell will wait, he will wait. If the majority of the tree says Russell won't wait, he won't wait. That's going to be my answer. Do you see what I just said? So instead of having one tree, you will have a forest of trees. Now, how do I generate this forest of trees? One idea, of course, is to run the decision tree algorithm k times. Is that reasonable? So instead of running just decision tree algorithm one time, you run it k times. How many of you think I can just run the decision tree algorithm k times? Somehow I think my tone, okay, good, thank you. But somehow my tone, I thought, gave it away. But if you run it k times, you'll get the same tree k times. It's a deterministic algorithm. Modulo type breaking. Do you understand what I'm saying? So if you're doing it k times, you at least randomize something. What will you randomize? So it's not just a forest, it's a random forest. Now what are you going to randomize? There are two things that you can do. One idea is basically actually an idea called bagging. Okay, this is an idea called bagging, and this goes all the time with another idea called boosting. Bagging and boosting are the ways you improve learning algorithms. So bagging idea basically says, if I have, let's say, 1,000 training examples, I split it into k subsets. Learn a decision tree for each of the subsets. If the entire training example is supposed to be representative of the concept, if I make it into k examples, if I make it into k subsets, just sample them, not just the first k necessarily, just take k, a subset of them, take them, another subset, so k samples, k subsets sampled from the original data, and I train a decision tree in each of them, they are going to be different. Even though your decision tree algorithm is deterministic, since the training data is changing, you will learn a different tree. In the case where there is, in fact, the training data is highly uniform, capturing exactly the same concept and has no noise, etc., you'll wind up getting the same tree. But in the case where there is noise in the data, training data, this can help you avoid overfitting to the training noise. Right? Mm-hmm. This idea is called bagging. Very good idea. There is an even more amazingly great idea which goes hand in hand with bagging to give you an idea called random forest, which, by the way, are used today everywhere. It's like used in large numbers of, any grad student tries to do anything nowadays, they'll try to start with random forest. And companies are below grad students most of the time. They're probably trying to just learn a base classifier. But if they do, they'll go all the way up to sometimes random forest. So what the random forest does is, in addition to taking a random subset of training examples, when you are constructing a tree, you only take a random, at any time, remember, at any time when you are constructing the tree, you are comparing, here for example, I compared two attributes, patterns and type. And I'm showing this, you pretty much realize that I would have counted this for patterns, type, and every one of the attributes, and picked the one which has the highest gain among all the attributes. But really what I showed here is, among these two, this was better. So what I could say is, I will just pick, at any given point, I will just pick m of the n attributes randomly. Mm-hmm. Act as if I'm only supposed to maximize on those m attributes. Do you understand what I'm saying? Yeah. Just m of the n attributes. Now, these ideas, if you figured out how to write the decision tree learning algorithm, that took probably almost 15 lines of code. Adding these is extra line of code. Yep. Very simple ideas. But it changes the effectiveness of decision trees tremendously. And if you are wondering why, say, well, we were supposed to do Bayesian learning. If we did Bayesian learning, we would have kept all the decision trees. And normal decision tree learning is just keeping one. Somewhere in between, I'm keeping some subset of the decision trees. And I'm generating these decision trees by training each decision tree each time on a subset of the training data. And whenever I'm training, whenever I'm picking an attribute, at any iteration and I'm picking an attribute, First I pick m of the n attributes and only consider which of those m attributes are the best and split on them. Right? So it's as if the other n minus m attributes, it's as if they don't exist as far as you're concerned. Why is this interesting? Because if there were irrelevant attributes, they might wind up not being considered by chance this way. And as dumb as this idea might look, first of all, I'm telling you it works, so you should believe me. And it's a very simple idea. And a variation of this simple idea is also one of the three things we'll talk about as to why people suddenly thought deep learning is working now, given that multi-layer neural networks existed for quite a long time and they were not going anywhere. What has changed? And one idea is what's called dropout in neural network learning. And it looks almost exactly like this. When you're training with respect to the samples, you'll act as if some number of nodes don't exist. So you remove that part of the network away, train only the other nodes, and then you bring them back later. And all of these, in essence, the reason they work is because Bayesian learning is the right idea. And we couldn't do it because it's too costly. This also tells you that maybe there is a way of doing full Bayesian learning in some cases at least. You are right. In fact, there are tons of things like, for example, things that I won't talk about here, for example, things like latent Dirichlet allocation, which is a specific type of topic models for text. That does full Bayesian learning. In some cases, full Bayesian learning is indeed feasible. Where it is not, rather than just go and say, I'll pick the maximum likely hypothesis, I pick K hypothesis. And of course, to generate the K hypothesis, I have to be clever. I need to make sure those hypotheses are actually different from each other. The way I'm making that they are going to be different from each other are two pieces. One, of course, is the bagging, because each decision tree is being trained on a different subset of data. Second is, at each time you are picking the most informative attribute. You're not looking the most informative attributes over all the attributes. You first decided M random subset, and you're only considering the best in them, among them. Again, this is the kind of idea would not make sense. I mean, it works well. I mean, in fact, I didn't even bother putting actual results, but random forest is pretty much the only idea that really works among the decision tree class of ideas. Everybody uses it, right? And the reason it works would not be understandable if you don't understand Bayesian learning, which we spent last time talking about. And that's the thing that you would have liked to do if you knew how to do it efficiently. But if not, this is a better way than just picking one hypothesis. Okay, yes, you had a question.
I think by your terminology, you explained it, but for the tree, you'd only use the M attributes for the whole tree, not just the first one, right?
No, every time I'm about to, basically, whenever I have this kind of a decision to be made, that is, I am stuck at I'm calling a decision tree, so I have a node and I need to split it.
Right.
So first I ask, before I split, I basically only send, for each recursive call to the decision tree, I won't send all the attributes, I send a random subset.
Okay.
So that entire recursive call only uses that random subset.
Oh, okay. All right.
This is basically random projection of the data into different subplanes. And it winds up actually making a big difference, partly because it might by chance ignore irrelevant variables, and partly also because it actually keeps track of multiple hypotheses and and what they are saying about the data. Yes.
You're splitting up the training data and you're splitting up the features, but is it important to make sure that over the K number of trees you're building, you consider at least once all of the
data,
training data, and all of the features that you
all of the features will be done anyway because it's random. So you're randomly selecting M. So to the extent the random selection is not biased, you basically have, everybody has the chance of being picked among these M. Okay, that is taken care of. The other question is the training data. You basically can essentially just partition it into K random subsets. Notice that the training data doesn't change So if I take the training data and split it into k partitions, there will only be k decision trees I will make. For the first decision tree, I have just the first partition. The way I construct the first decision tree is whenever I'm about to split, I always pick random m attributes and see which is the best one. And I do that across. So there's a large amount of variation going on. It looks as if, why are you just giving away information that is available? And it only makes sense in the context of the discussion we had, which is you can have large amount of irrelevant attributes. You can have large amount of noise. And both are somehow being handled by this tree. Okay? And of course, the guy who came up with the idea of bagging is pretty famous. This guy called Leo Breiman. He's a statistician. It's a very, very useful idea to know. Yes, there was another question.
Yes. Just real quick, so on the subject of picking the random subset of attributes, right? You do it randomly each time you want to make a decision.
Exactly, yeah.
And are we getting like a speed up in computation?
No,
Is it focused on the diversification of the tree population?
Accuracy. So random forests are never going to be cheaper than finding one decision tree. It's a good question, but don't ever ask it again. If you understand today, you should never ask that question again. It's a very good question. Other people who didn't ask probably weren't thinking at all. Okay, so I'm not giving you any benefit at all. All these ideas, if you're comparing Bayesian learning, which is the right way to do learning, to normal learning, which is picking one hypothesis. Bayesian learning is better because it has higher accuracy. But we don't do it because it takes too much time. So random forests take much less than the Bayesian learning, more than just finding one decision tree, and yet they give higher accuracy than single decision tree.
Makes sense.
Yes?
Isn't the decision tree a relaxed version of a Bayes network?
It's not, but the next thing we talk about would be. Well, you could see not so much actually. I think keep that kind of a thread in your mind, but we'll talk about neural nets, and I'll show you that they're just relaxed versions of Bayes nets. But thinking like that is something that I highly encourage. Of course, if you think too much of that, you become the John Nash when he was crazy, not before he was crazy. You'll start seeing patterns where there are no patterns. But, basically there's this quote that I really love, that good mathematicians see patterns. Better mathematicians see patterns among patterns. Good mathematicians see analogies among fields. Better mathematicians see analogies among analogies. Okay? And of course, at some point of time, you also become crazy, and John Nash part. How many of you have seen Beautiful Mind? Okay, and it's great. I mean, he was looking at all these great patterns. He was overfitting the data that he was making up in his head. It's amazing learning going on. But there is obviously somewhere in the right place to stop. But the idea of asking yourself, why did we do this, and how is this connected to something else we did in the course, this course, or in your entire life, is something that you have to do. Otherwise, each of these are compartmentalized parts. You won't become schizophrenic, but on the other hand, you're not learning anything either. You're not connecting things across. Any other questions? Yes?
This is probably a tangent, but where does a support factor machine fit into this?
It will fit. It'll all fit if we stay for extra 3-4 hours. But that's the thing. What we will do is take a break. So given that it's Thanksgiving, I thought I should not get exams. That's not a particularly good way of giving thanks to you guys, because some of you didn't do well. But there are some raspberry bars. Help yourself. And in particular, how many of you here have attended every one of the classes till now? Thank you. The rest of you are just getting it free.